Hello, and welcome to my presentation of my group's project proposal. My name is Trisha Bandril, and I am speaking on behalf of my group, Colleen, Lally, Rosio, Patino, and Margaret, Saltysiak. We are students of Benedictine University under the Department of Public Health. Under the instruction of Professor Jennifer Makelarski, I am presenting to you my group's project proposal depicting a linear regression model. With that, I begin with our research question of, is maternal weight gain during pregnancy affected by marital status and maternal age? Our question aims to look at the relationship between the mother's marital status and age, and how these factors or variables may or may not have an effect on the weight gained by the mother during their pregnancy term. The data utilized for the purpose of this research comes from the guidance of the 2018 User Guide to the Natality Public Use File from CDC. The data was collected by the National Vital Statistics System, or NVSS, which is maintained by CDC's Department of National Center for Health Statistics, or NCHS. The dataset has about 1,000 data points. The data points notated with a 99 on variables used have been excluded for a more accurate interpretation of findings. Here we have 3 variables, 1 dependent variable and 2 independent variables. Our dependent variable, which is maternal weight gain, is, according to the user guide to the 2018 Natality Public Use File created by CDC, the weight gained by the mother during their pregnancy is derived from their pre-pregnancy weight and their weight at delivery. The mother's pre-pregnancy weight is subtracted from their weight at delivery to determine the total weight they have gained during their pregnancy term. The mother's weight is reported in pounds. Our independent variables are marital status and maternal age. Marital status. We are approaching this research to determine whether the weight gained by the mother during their pregnancy term is an effect of their marital status. Maternal age predictor variable. While determining whether the weight gained by the mother during the pregnancy term is an effect of their marital status, does maternal age affect the mother's weight during their pregnancy term in correlation with their marital status? In our approach, we are determining a linear regression model that estimates the relationship between maternal weight gain and marital status during a pregnancy term by using a predictor variable such as maternal age. Our hypothesis is then that marital status and maternal age have an effect on maternal weight gain during pregnancy term. Here are some key points in our dataset. Some data points that are missing values and or have high levels of skewness are seen in our dependent variable of weight gain. 99 is categorized as missing data. Also in our dependent variable of weight gain, it has unusual high values such as 52, 40, and 60 pounds. For our predictor variable of maternal age, the minimum value included in the dataset is 15 years old, while the maximum value included in the dataset is 47 years old. We are also taking into consideration some factors that the data may not represent accurately, and those are unmarried mothers who cohabitate with their partners, unmarried or married mothers who are not in a cohabitation with their partners, maternal age of married mothers at the time of pregnancy term, maternal age of unmarried mothers at the time of pregnancy term. With that, my group and I are hopeful that our research will produce valuable statistical inference to help decide whether the regression model will depict a significant relationship between maternal weight gain and marital status.
Descriptive statistics is as followed. We have a mother's age with a maximum age of 47, a minimum age of 15, and a mean of 29. Mother's weight gain was at 98 maximum and 0 for minimum. These numbers, when we represent a 0, that means a zero weight gain. difference. There wasn't an increase or decrease. That mother just had a 0. Anything that was marked as missing would be coded as 99. That's why we have a maximum of 98 with the standard deviation of 15.5%. 15.5. For marital status, we have the frequency and the percentages. We also have valid and missing. So for our valid units that were used was at 532, which is a 55.2%. Unmarried women were at 325, which was a 33.7%, with a total of 857 frequency accounted for. For our pairwise scatter plot, we have our independent variable, which is mother's age and falls on the x-axis. We have our dependent variable, which is mother weight gain during pregnancy, that falls on the y-axis. The independent variable is illustrated in the scatter plot in years with increments of 5 years, while the dependent variable is presented in pounds with increments of 20 pounds. Based on the graph, one can interpret the data point clusters around the means of both variables. In addition, one can depict the spread of the data points based on the standard amount of deviation from the means. When this is out in an equation, we have y equals 32.5 plus a negative 0.120x. Next, we have our regression of standard error and our coefficients of standard error. Our correlation coefficient, which is our R, is 0.045. This measures the strength of the linear association between the two variables, which is mother's age and mother's weight gain. The R value is very close to 0, which suggests that there is no association between the mother's age and the mother's weight gain during pregnancy. Our R squared, which is a coefficient of determination, is 0.002. Multiplying this by 100, we get a 0.2%. The difference of mother's weight can be explained by age. There is a lack of variation here. Our standard error of estimate is 15.5, and one can predict that the weight gain by mothers at the end of their pregnancy is a plus or negative 15.5, which is multiplied by 2 and results in 31.0. In this slide, we will be talking about our coefficients, which represents our parameters. We have a constant of 32.5, which signifies that at 0 years of age, we should be having a weight of 32.5. Our significance is at 0.161, which is above our 0.05 threshold. The intercept is not meaningful due to the logic that mothers cannot be at the age of 0 and have a 32.5 starting point. It does not explain the difference, and the slope is not meaningful. We have to go with our null hypothesis that the slope is equal to 0. There is no relationship between the mother's age and weight gain during pregnancy.
Before we continue with our linear regression, we need to make sure that our variables meet 4 assumptions. The first assumption is that the probability distribution of random error at each value of x has a mean of 0. The probability of being above or below the regression line in that distance has an expected distribution that centers around 0. When looking at our scatter plot, the residuals seem to have similar amounts above and below the line and average out to 0 as we move across the scatter plot from left to right, so this model does not violate this assumption. The second assumption is that the probability distribution of random error at each value of x has a constant variance. The data points on the scatter plot are spread evenly across the regression line from left to right, so the variation in random errors should be similar. For our model, the vertical variation of the residuals are similar as we move across the scatter plot from left to right, so our model does not violate this assumption. The third assumption is that the probability distribution of E at each value of x is normal. If we took all of the possible values at any point along the regression line, the values of x along the regression line would form a normal bell curve. Most of our points are close to the regression line, and the probability of being further away from the regression line becomes smaller as we move out from the bell curve. Our interpretation is that the histogram shows that the residuals fall under a normal distribution, as does our QQ plot on the next slide, and therefore our model does not violate this assumption. The fourth and final assumption is that the value of E for one observation is independent of the value of E for any other observation. For our different visualizations of our model, the residuals look random and do not appear to have a systematic pattern, so our model does not violate this assumption. So to summarize our model diagnostics, our model follows all 4 assumptions, so we are able to proceed with linear regression analysis.
Because we are examining the impact of 2 independent variables and an interaction variable, which was categorical, on the outcome of maternal weight gain, a between subjects ANOVA was an appropriate hypothesis test. The goal was to determine if there were statistically significant differences between the groups. When looking at the tests of between subjects effects, only the p-value for the intercept is significant. The p-values for beta 1, marital status, beta 2, mother's age, and beta 3, the interaction variable, are all greater than alpha and therefore are not significant. Because the significance level for each variable and the interaction term are greater than alpha, we cannot reject the null hypothesis that the slopes equal 0 at all levels of the interaction term. When looking at the parameter estimates, at 0, the intercept is 38.15. The regression standard error for the categorical variable and the intercept is large, suggesting poor accuracy with prediction. The interaction standard error is small, suggesting a much more precise prediction. The significance levels for all variables is greater than alpha, meaning that we cannot reject the null hypothesis. The confidence interval is wide, suggesting a greater range for error in prediction. When looking at the scatter plot for the multiple linear regression, the scatter plot demonstrates almost no linear association. Maternal age is not related to pregnancy weight gain. Pregnancy weight gain is not affected by marital status.